Okay, thank you very much, James. And good morning, everyone. And welcome to the first session of the Breakthrough Discuss 2022 workshop. As James mentioned, the topic for this session is affordable and innovative concepts for cosmological measurements. My name is Philip Mauskopf, and I'm from Arizona State University and the co-host for this session, along with, as James just mentioned, Professor Suzanne Staggs, who is there with you from Princeton University. I am disappointed not to be there with you in person, but as you can maybe tell from my voice, it was finally my turn to see the dreaded double red lines on my home COVID test late last week. And so, unfortunately, I'm missing all of the in-person conversations and in-person events that you guys are enjoying, hopefully. But to begin the session, please allow me to set the stage for our discussion of innovative and affordable cosmological instruments and missions by giving just a story with no slides, like we're continuing the theme, but the story of our current understanding in very broad strokes of the cosmological model, given that we have a broad audience. Some of this story will no doubt be repeated by some of the speakers and their motivation for their own particular areas that they're talking about. But in broad strokes, our story, the story of our universe, begins in a small volume of space, perhaps around the beginning of time, when there developed just the right conditions needed to set off an exponential and superluminal expansion of the fabric of space-time, an event known as cosmic inflation that turned our tiny volume of space into a vast expanse unknowingly larger than the size of our current visible universe. As this cosmic inflation was happening, only any pre-existing wrinkles in the curvature of space were being expanded and smoothed, and the density of any pre-existing particles and their associated temperatures were all driven to zero. The end of this process was triggered by some sort of phase change or decay of these mysterious forces or fields driving the expansion. And this decay converted the driving energy back into more familiar forms of energy to us, particles of all types, including those of the standard model of particle physics. And this converting of this driving energy into normal particles is known as cosmic reheating. The dynamics of this expansion and the end of the expansion also likely produced gravitational waves, like ripples on a pond from a stone or the ringing of a bell will produce waves which then slowly decayed away as the universe continued to expand at a much lower rate. And these would be known as primordial gravitational waves. The cosmic reheating produced matter throughout the now slowly expanding universe. And this matter had small and random variations in density, but initially no average bulk motion. And all of the particles, after reheating, began to interact with each other. And the large range forces, of course, were dominated by gravity and radiation pressure. Throughout this process and the subsequent expansion, there are a number of milestones that are notable. First of all, various relic particles freeze out or froze out during the expansion and stopped interacting through radiation pressure, for example, and only continue to interact gravitationally. These particles include things like what we now think are dark matter particles and other weakly interacting particles like neutrinos. In addition, over time, the baryonic particles, which have antiparticles, annihilated each other um, leaving a very small residue, not of particles. But their annihilation products that left a thermal bath of photons. And this is what we see today as the cosmological background. And it's worth noting, we can measure and count the numbers of particles. And if you assume that in the initial reheating, there was sort of one of each randomly produced, on average, the same number. But today we can count, and there are about 10 to the 9 photons in the universe, mostly in the cosmological background per baryon. Another thing that happened is that, or that we've observed, is that there is some residual now in the current universe, inflation-like force present, or dark energy that appears only to affect the expansion of the universe. It's only seems to, well, it's only been able to be observed affecting the expansion of the universe in the fairly recent past history. And so there's a constraint on its, how much of this inflationary style dark energy is left. And then finally, of course, there's the entire history of the evolution of all structure in the universe, dominated by gravitational collapse, causing the formation of from baryonic matter, hydrogen, gas in the universe, forming stars, galaxies, planets, and life, as we know it here on the Earth, at least. So that's the story of cosmology. That's the background for this session. This story, as told there in very, very broad strokes, has taken shape during my lifetime, mostly through the work of many theoretical and experimental cosmologists, including a large number of them in the room there with you, working on many different aspects of the story and obtaining evidence for the different details. And to me, it's very impressive to have witnessed a lot of the developments myself, and then in perspective to realize that how far we've come in such a short time. We've come from, having a model of believing the Earth to be the center of the universe hundreds of years ago to now facing the fact that currently our evidence indicates that we don't even know the properties of the particles or the constituents of the energy that make up the majority of the universe. The idea of cosmic inflation was first proposed about 40 years ago, and now this is sort of known as the standard model of cosmology. When I was a graduate student, and since we had the speeches from people in the Bay Area, I should note that this was at UC Berkeley, where I was a graduate student. There were debates about whether the Hubble constant was, the value of the Hubble constant was 50 kilometers per second per megaparsec, or 100, were the two camps. And if the universe contained only baryons, and whether or not the curvature was open or flat or closed. And today we have, I would say, consistent evidence for the existence of dark matter and dark energy from a variety of cosmological observables. We have precisely measured many of the parameters of the standard model of cosmic inflation, such as, many of these discoveries, and this is part of now getting to the point of this session, many of these discoveries have been made through relatively small teams, and with fairly low-cost experiments at the limits of technology. However, many questions and mysteries still remain, such as the nature of dark matter, the existence of primordial gravitational waves, the imprint of annihilation of different particle species in the cosmological background, the properties of neutrinos, properties of dark energy, the growth of supermassive black holes and galaxies and feedback, and many, many questions are still out there to be solved. And there's many approaches to solving these questions, and not only small teams and innovative approaches are the only ones. Obviously, there are many large efforts also involved. But for this session, we have gathered 6 leading researchers to have a discussion about what we may learn over the coming decades and how innovation, so the emphasis I think here is on how innovation can continue to drive discovery. And so with that, I will say thank you again for listening, and I will hand off now to Suzanne Staggs, my co-host, who will introduce, make some comments and then introduce the first of our panelists and speakers. Thank you.